This section covers some of the differences that you can encounter when porting software to a MIPS processor. Here's what I'm going to cover. Endianness, what is it? I'm going to review the cache issues. I'm going to talk about odd data alignment. I'm going to discuss the use of short variables. I'm going to warn you about the type character in your code and the use of bit fields. In Jonathan Swift's Gulliver Travels, the little Endians and big Endians fought a war over the correct end at which to eat a boiled egg. Danny Cohen used this analogy for a paper he wrote in 1980 entitled On Holy Wars and a Plea for Peace. The paper covers the topic of byte ordering in computer systems. While it didn't stop a war, it did coin the terms Little Endian and Big Endian. These two tables show the differences in the two methods of ordering. Integers or words don't come out any differently, but shorts and characters are arranged within the words in a different order. A MIPS CPU can be set to work in either Endian, and there are instructions that can be used to swap bytes within words efficiently. Those instructions, load word right and load word left, are covered in the instruction section of this course. So long as the binary data is never imported into your application from elsewhere, and you can avoid accessing the same piece of data under the two different Endians, your code is portable. Beyond that, the subject is covered in detail in the Danny Cohen paper, which you can find on the IEEE website. It's also covered in Chapter 10 of the C MIPS Run Linux book. On caches, virtual, and physical memory, here are some reminders of the things covered in various sections of this course. In regards to DMA, the caches are not coherent, so you must invalidate cache lines for an incoming DMA and flush cache lines to memory for an outgoing DMA. If you are loading code into memory or modifying on the fly to cache addresses, you must use the synci instruction to sync the instruction cache with the data cache and memory. Remember, the page size needs to be as large or larger than a way of your cache to avoid cache aliases. All memory accesses are virtual. Some are direct mapped, and some are mapped through the use of the TLB. Accesses to unaligned addresses cause an address error exception. The address accessed must be aligned to the instruction type. The load or store word instructions need to address on a 4-byte boundary. Load or store half-word instructions need to address on a double byte boundary. Only loads or store byte instructions can access any byte address. The compiler takes care of most of this for you unless you are typecasting. Typecasting a small type to a larger type can lead to unaligned accesses. For example, casting a byte that is aligned in the middle of a word to a word will cause an address error. To get the compiler to warn you about the possible unaligned typecast, use the -wcast align option. There is a supplied exception handler that you can use to catch address errors. But to be more efficient, you should really fix the alignment in your code. All arithmetic in a MIPS CPU is done on 32-bit values. Any instructions that do arithmetic on values less than 32 bits are synthesized instructions and will translate into multiple machine instructions. You may think you're saving space by using a short for a loop counter or an index into a small array, but in fact you're adding at least one 32-bit instruction to do a conversion from a short to an integer and taking a performance hit. When you are porting code from a 16-bit CPU to MIPS, you need to use integers that are 32-bit. If your code relied on a signed bit being bit 15 to catch an overflow, you will have to change your code to check bit 31 instead. MIPS compilers default the character type to unsigned. This has caught some programmers out because they use a character variable to hold the result of a function that can only return a 0 or a -1, and the default character type will never look like a -1. The compiler can be changed by using the -f sign char option. Bit fields often vary from one compiler to another. When you define bits in a bit field, you should always implicitly define each field as signed or unsigned. The GCC compiler will default any non-implicitly defined fields as signed. For MIPS, it's harder to process signed fields than unsigned. You can switch the default to unsigned by using the -f unsigned bit fields option. This ends the Porting C section.